3 years, in the last 3 years, so a large amount of works that explored all the effects, theoretical and also some possible observational constraints, which indeed we can derive for the jet structure. The most simple jet structure we have been dealing with also yesterday in the lecture is that of a uniform jet, which is shown here as an example. That's a top hat jet, also called, and in principle, the idea is that within the opening angle of the jet, the energy, kinetic one, and bulk clearance factor is constant and independent on the angle. This was the jet we discussed yesterday, and we saw that if this jet is seen even slightly off axis, the reduction due to the relativistic beaming of the radiation is quite severe, especially in the prompt emission. This can make the prompt almost invisible because of the strong reduction, which depends on the value, essentially on the value of the bulk clearance factor. In the afterglow, this effect can suppress the very, very early emission, and according to how off axis we are, it can make the burst appear as a transient, let's say, becoming visible at progressively later times, the more off axis we look to that. The core of, in my opinion, of interpreting the GLB population with a uniform jet is the fact that in order to justify and interpret the diversity of the properties of GRBs, like, for instance, the observed energetics, but also other properties, people thought about having within the population GRBs with quite different opening angles. If you want, a very simple argument is related to this equation here that also we discussed yesterday, since for years we have been using, and still now we use as a proxy for the energy of the burst, the isotropic equivalent energy. But once we measure the jet opening angle, we can recover the true energy value by multiplying by the square of the opening angle in the small angle approximation, which, according to some observations, is almost constant. By then using this argument here, one is led to think that there could be, let's say, a relation with the most energetic burst having the smallest opening angles. But already in 2001 and 2002, people started to think about another alternative, which is, as I said, very appealing because it brings to a kind of unification within the GLB population. The idea is that of having, and today maybe we will discuss this a bit more in detail, which is indeed, let's say, expected from the theory, having not a uniform jet or top-hat jet, but having a structured jet. And the simplest way of thinking to this is that of nesting one within the other jets with different opening angles, and of course with different energetic and bulk clearance factor. In the continuous limit of this, let's say, discretized sketch, you can think about the smooth distribution with the, let's say, a couple at least of possible structures that describe an energy and the bulk clearance factor, which typically decrease from the core of the jet, going to larger angles. The interesting point of this model that was first described and developed in detail for the prompt and afterglow emission in GRBs by these two papers is that the observed diversity of GRBs can be interpreted within, of course, the limits of some details, but can be interpreted as due to a different viewing angle, much like the, let's say, variety of AGN sources. In 2017, this idea was by far explored in order to justify the observed properties, especially the afterglow, I would say, emission of 1708-17, and we will see that today. But before going to that, since yesterday, if you remember, we described in cannot go back.
Normally you have to click on the slide and then it works.
Okay, thank you. So yesterday we saw the viewing angle effects on the prompt emission and on the afterglow emission that I just described, but assuming a uniform jet, okay, with basically working with the Doppler factor here. And now we can do the similar argument, but the, let's say, equations become considerably more difficult, so we will just understand the meaning. And here you see divided again the prompt and the afterglow. Okay, the let's say the core of a for the description of a structured jet is that indeed of describing the structure of the angular structure of the kinetic energy and of the Poincaré factor. In this example here, for instance, they are described as power law. There are some parameters, two of which describe the innermost part of the jet, the so-called core of the jet, which typically is assumed to be a region with an opening angle of a few degrees in which the energy and the Poincaré factor have the larger values and are almost constant. And then you have the power in this case. Other possible typical description is that of a Gaussian jet, in which you have to describe, in that case, the energy and the opening angle of the core. These values, especially the core opening angle for the gamma factor and for the kinetic energy, are not necessarily equal. So for the prompt emission, you can immediately understand that if we are located at a given viewing angle with respect to the axis of the jet, we have to consider in the emission we see not only, let's say, the emission produced by the snapshot of the jet surface, which is exactly aligned with the line of sight, but also with the possible regions which are closely located closer to our line of sight, whose beaming angle, so proportional to 1 over gamma, is large enough that their photons can be intercepted by our line of sight. So it's a kind of an integral that we have to perform. And the outcome is that if we compare in this plot the energy or the luminosity seen at a given viewing angle with respect to the luminosity seen exactly on axis, yesterday we described this curve here, which is valid for a uniform jet. And you see that instead, if we have a structured jet, of course, for a given viewing angle with respect to a uniform jet, in the structured jet, we can see a larger luminosity because we have the contribution not only of the, let's say, core of the jet, but which is minimal, but mainly the emission which is aligned to the line of sight, and possibly the emission of regions which are at higher latitudes with respect to our line of sight, whose opening angle, as you see in this sketch, is larger. So it's whose beaming angle is larger, and therefore they can be seen. Of course, the shape of these curves, as you can see, depends on the parameters of the structure. For instance, the most promising in terms of observing a larger luminosity, the largest luminosity for a given viewing angle is the case in which the structure of the Poincaré factor and the structure of the kinetic energy have the same core angle. If you vary their ratio, of course, you can obtain different slopes of the let's say off over on view. This is quite simple because in the prompt emission, the game is done by, let's say, giving a prescription for the kinetic energy and the prescription for the Poincaré factor, but they are both independent of time. When we go to the afterglow, we have also to account for the fact that the afterglow is decreasing as a function of time. So sorry, the Poincaré factor is decreasing as a function of time. And as well, the kinetic energy we have to account has to be computed at each step according to the shock which is developed and the fractions of energy that we distribute to the particles and magnetic field. Overall, in this plot, you can grasp the general message, which is very similar to that of the prompt emission. So if you compare, for instance, these lines are for uniform jet and look to the, let's say, black one with respect to the violet, which is for 1.5 times the opening angle of the core of the jet, or larger viewing angles. You see that in the uniform jet, of course, you have a strong suppression of the emission at early times, and instead for a Gaussian jet, or a Gaussian jet with some variation, constant or not, for the bulk currents factor, but it doesn't matter, you see that the corresponding color lines in the two plots show a quite different flux. So let's say the structured jet is advantaged with respect to the uniform jet, because indeed you have always some part of the, let's say, emitting surface which is aligned with the line of sight, and you have also the contribution of regions which are not necessarily aligned with the line of sight, but contributing because of their relatively wide beaming angle. I hope I made it simple enough. The bottom line is that different prompt and afterglow properties, of course, for the structured jet are strongly related to the structure of the jet. Compared to the uniform jet, of course, we have more free parameters to assign to the problem, and of course, this means that not always it's possible to constrain them all. I would say that the only clear example in which this was possible with a reasonable accuracy is indeed the jet of 17017. The last slide I had yesterday, which was just a kind of final slide because we followed this kind of parallel description of the population of long and short GRBs, was related to their, let's say, more cosmological properties as a population. And this is summarized here, where I reported the two fundamental functions that are typically used to describe these sources and their cosmological, and their local rate. So let's start from the top plots, which show the luminosity function, which as many other sources, it's described by a power law, quite steep decaying as a function of the luminosity. This is important because it's telling us that large energetic or luminosity events are fewer than low luminosity one. And yesterday we discussed that this is indeed something to take into account when we want to understand the observed energetics, because selection biases like the flux limit of the instrument we use is relevant. For short GRBs, here I show you a plot which, if you compare the two, apparently have a similar, let's say, luminosity function. There are works that say that probably the bright part of the events is somehow flatter, with let's say, the possibility to get these points here, which, by the way, are those determined by the detection of GRB 170817, for instance, within the context of a structured jet. But I have a slide later today regarding this as well. As far as their redshift distribution, yesterday I showed you the observed redshift distribution, which is a biased representation of the intrinsic one. For long GRBs and short GRBs, we have this, let's say, nice general concept that is related to their progenitor. So let's start with the short GRBs. In general, if you consider the formation of stars as a function of redshift, so the cosmic star formation rate, which is represented by these, by this thin line here, the intrinsic, the population redshift distribution should have a distribution with peaks in redshift at lower redshift due to the delay between the formation of the progenitors, the double systems that probably follow the star formation rate, and the merger instead, which can take several mega years. On the side of long GRBs, instead, we have a kind of opposite effect, because with respect to the cosmic star formation rate, which is the thin line here, their redshift distribution is, let's say, steeper. So there is a deficit at low redshift, the peak is likely at higher redshift, and then more or less they are similar at high redshift. And this is due most likely to the effect that let's say, the progenitor of GRBs, we think should be a star with a relatively low metallicity, and therefore it's less favored in the local universe where the metallicity in general is larger. The reason being the fact that for a smaller metallicity, the star, which is a rotating star, has less chances to lose its angular momentum through winds during its life, thus keeping it and forming a highly spinning black hole, which is, let's say, more favored in extracting a larger amount of energy within a narrowly collimated cone, and therefore launching the jet. Here I report for you, just for reference, the rate of GRBs long and short with luminosity larger than a certain value. This value is chosen as a reference unit. And you see that these are quite similar, but again, remember that these are the observed, let's say, rates. What does it mean? Since these bursts have a jet, these rates are computed on the basis of the bursts that we see, which are mostly, I would say, bursts whose jet is pointed towards the Earth. If we want to know the intrinsic rate, we have to correct for the opening angle, which is very likely not a unique value, or it could be structure, and therefore this rate change accordingly, and they are in general larger. And this rate should be even distinguished from the observed rate, so the rates of GRBs detected by, let's say, flying instrument like Fermi and Swift, because in that case, on top of the combination of these two functions that determine the rate as a function of redshift, if you want, you have to account for the fact that these instruments have a limiting flux, which therefore allows you to see at different redshift only parts of this luminosity function with an increasing cut as you go at larger redshifts. Okay, so if there are no questions, sorry, this was the last part of the lecture of yesterday. If there are no questions, I start with the second lecture.
Let's see, so there are no questions in the chat. Maybe someone has a question. So I would like to ask one, if possible. This difference, let's say, this variation of the rate, right, with respect to the stellar formation in the long and the short. So is it possible to infer from that whatever give rise to the long GRBs is a different physical process than the short one, so that the short are typically a merger and the long are typically a stellar collapse, or it's going too far?
Well, it's a piece of the puzzle which points in that direction. It's not the only, of course. We have also, if you want, you can make a list. You have differences in the properties of the host of long and short GRBs, which somehow are consistent with this picture of having these two different progenitors. You have direct evidences or direct observations, like, in fact, I just mentioned it yesterday, the fact that in long GRBs there are associations with extremely powerful energetic supernova explosions called hypernovae, which have peculiar properties. And in short GRBs, we have these unique example, unique case, 17017, but which established the strong link between the possibility that BNS at least can launch a relativistic jet and be the sources, the progenitor of short GRBs. In general, there is also, let's say, there are more theoretical arguments related to the energetic of the sources, which are different, as I said yesterday, and these might be, let's say, related to the different amount of material that you have around that can form the disk, which could be the powering, let's say, fuel that can power the jet itself, not the only one, of course. And this could be, let's say, slightly different in the case of a long and the short GRB, if produced respectively by the core collapse and direct, more or less, formation of the black hole and the accretion then of the disk, with respect to the short GRBs created by the merger of two neutron stars, of a neutron star or a neutron star and a black hole. So it's just a piece of the evidence. There are others, but in general, the, let's say, idea seems to be well established. Not, I mean, I'm not saying that other possibilities are excluded. The possibility that long GRBs might have a channel of progenitor, which is due to binary system, is not completely ruled out, and there are works and in the past especially that considered that. But in my opinion, at the moment, there are no compelling evidences supporting this channel, at least for the long GRBs. For the short GRBs, on the other side, apart from the BNS, there is still great expectations for the black hole neutron star case.
Clear.
As a possible other channel of progenitor.
So I see no other question. No, so please go ahead with the second part. Thank you very much. Okay, so Chiara, my idea is that of, let's say, splitting this second lecture into two parts. The first one, I will basically discuss 1708-17, and I divided the lecture into two parts. The first one is mostly devoted to the presentation and discussion of the GRB-related electromagnetic components. So I will start with afterglow emission and then slightly discuss the prompt emission. And then the second part is related to the kilonova component. So we can take the break, if not too late, after the end of the GRB component discussion and presentation. Perfect. Okay, so let me just make a very brief summary, like the one we had for GRBs, a kind of summary slide where you see the fundamental, the milestone for the subject, in this case 1708-17, which here are let's say listed also with their time scale. So you know that after the end of the detected signal in the gravitational waves, there was a detection with a delay of about 1.7 seconds of a short GRBs by the Fermi satellite, confirmed by the integral satellite. The short GRB has this property as far as the prompt emission is concerned. It is delayed. Disappeared. Sorry. Sorry. It is delayed by 1.7 seconds. Its duration is composed by a short spike of half a second, which is slightly harder and bearing a larger luminosity. There is the possibility that this short spike is followed by softer emission at kind of a tail, whose spectrum could be thermal, even though with no that much compelling evidences. 11 hours roughly after the discovery of the GRB, the kilonova emission, bright, transient, fast evolving in color from blue to red, was discovered, as well as its location within a nearby galaxy, NGC 4993. The kilonova is, as I said, a fast color evolving transient with the luminosity which is roughly bolometric 1 10 to the 42 per second, and evolves as a function of time, decaying bolometric luminosity as t to the minus 1/3. The host shows an old stellar population and is quite massive compared with the host of other short GRBs. And the location of the source, projected one in physical units, is 2 kiloparsec off center from the center of the galaxy. Now, 9 days and 16 days after the short GRB or gravitational wave event,
there was the discovery of another counterpart, first in the X-rays at 9 days, and then at 16 days in the radio. Before these dates, of course, people searched for this counterpart with deep observations. Deep upper limits were obtained, but no detection. But starting from about 10 days then, with the detection of these counterparts, a strong follow-up observational campaign started, which was more successful in the radio band and slightly less successful due to observational constraints, for instance, in the X-ray band, which followed the emission of the source up to years after the event, and also very recently, by the way. And this is the afterglow emission. The afterglow showed a more multi-wavelength long-lasting emission characterized by a slowly rising phase, T to the plus 0.8 roughly, with a peak quite late, 150 days, and let's say crucial observations were provided by the radio high resolution imaging, which revealed the proper motion near the peak of the electromagnetic emission, which was then followed by a fast decay. So this picture, and the bottom line here, is the fact that, as I will tell in a moment, the interpretation of this event evolved with the discovery of the properties of the electromagnetic emission of the source. And let me say that, in my opinion at least, a lot of the ingredients necessary to interpret these electromagnetic emission components were already in place, but their application required some revision of our thoughts of the theoretical picture. And of course, there were many, many advances in the understanding of both the, let's say, kilonova emission and the link with the rapid neutron capture nucleosynthesis, and the way this can power the emission we see of the kilonova, as well as the emission of the gamma ray burst itself. So in a quite pedagogical approach, the first thing we thought and we should think is how this gamma ray burst compares with the others. Here you see a nice plot. I forgot the reference. This comes from the recent review by Margutti and Chornok. And you see in the insert the light curve of the event, split into two energy bands, a soft one, let's say, and a harder one, which shows the detection, let's say, of the main spike, and then this possible soft, because you see it's slightly more, it's brighter in the soft band tail, which continues for a few seconds. Given the measurement of the distance of the source, the position in this plane that we saw yesterday, where now here I just show the few, let's say, short GRBs with measured prompt emission properties and redshift. The position of 170817 is quite displaced with respect to the other short GRBs. It has, in particular, an energetic, which is 4 orders of magnitude smaller, roughly, than the average value of short GRBs, and its peak energy, that you remember characterizes the peak of the SED, is in the low end, but not extremely soft with respect to the others. The position of the burst probably here immediately raises the comparison with the other GRBs, because under the assumption that these GRBs are collimated events whose jet is pointed towards the Earth, this burst is, of course, inconsistent with this picture. I explain this better here, where just based on the expected luminosity that it should have if it were a normal GRB, short GRB, we are orders of magnitude, we have a source which is orders of magnitude lower. Also, the afterglow emission is against this possibility, having a jet aligned to the Earth, because in that case, we should observe, like in many other short GRBs, which are represented here in gray points. This is the afterglow emission X-ray 1 as a function of time, should decay roughly as a function of time with a power law, which is t to the minus 1 or something like that. And in this case, this is not observed because, as I said, up to a few tens of days, no afterglow emission for this event was found, even with upper limits in the X-rays, in this case, which were quite deep. And if the afterglow was at the level of the typical short GRBs, it should have been detected at least at these epochs here, or even earlier. There is also a general probabilistic argument, because if we take the typical opening angle of a GRB and we are even more conservative, assuming that it is larger than the typical one, I showed you yesterday that we have very few measurements of the opening angle. So let's assume 10 degrees, the probability that the jet is aligned to the Earth is quite small. And given the small distance of the source, the probability that this happens within such a small volume is even lower. So this general consideration led people to think that we should exclude this possibility. So I open the parenthesis, given this was the first short gamma reversed associated with its putative progenitor, you know, on the one side, it was very exciting to think about alternative. On the other side, all, let's say, the observational evidences we had for the population of GRBs, in a way, were excluded, at least for this possibility. So the obvious alternative, which is very likely, appeared very likely, is that we are observing the jet off axis for the consideration we did yesterday. In that case, we have a strong debeaming if the jet has a typical Lorentz factor of a few hundred, and also the afterglow should not appear bright in the first phases, because basically the beaming angle 1/gamma is smaller than the viewing angle, so the off-axis viewing angle. When gamma 1/gamma, so the beaming, because of the deceleration of the afterglow, becomes comparable to the viewing angle, we should see the peak of the afterglow. And for let's say with some very easy computation, the appearance of the afterglow at 10 and 16 days was apparently interpreted as the peak of the afterglow. The point is that, as I showed you yesterday, the expectation was that from this moment on, the observer off axis should see the decay of the afterglow emission as any other observer would have seen if located on axis, okay? So like moving along this line here. The off-axis case was also giving a first, let's say, interpretation of the delay between the gravitational wave and the electromagnetic emission. You can understand this in this sketch here. The gravitational waves are traveling this direction towards the observed, whereas if the jet is misaligned with respect to the line of sight, and you think about its, let's say, dynamical evolution up to the transparency radius that we worked out yesterday, this is where it releases its radiation, and therefore there is a delay, which is basically this distance divided by c, between the gamma ray, between the detection of the gravitational wave and the gamma ray. And with some, let's say, computation, it was demonstrated that this could be consistent with the observed 1.2 delay. So what I'm saying here is what we thought, I would say, more or less after 1 month since the discovery of the source. But this picture was completely falsified by the, let's say, detection and follow-up of the emission in the radio band. In fact, the follow-up by Mule and collaborators with the JVLA at frequencies around 3 gigahertz showed that starting from the first detection of the afterglow, up to 100 days or so, the emission of the afterglow, instead of decaying as expected if we were just observing a uniform jet of axis, was increasing. So the opposite of the expectation. And the increase was quite shallow, t to the plus 0.8. Why I say quite shallow? Because, well, if it were faster, we could say, okay, we are more off axis than what we thought. And so the initial emission we saw probably was still in the rising phase, but then we should see the decay. So maybe it could be like this, but this was not working as well. So the long lasting and shallow increase of the flux as a function of time was in a way excluding any possible, let's say, uniform jet off-axis case. And people then started to think about the possibility that instead we are dealing with a structured jet, because in the structured jet, very simplified model, which I described to you before, you can think about that as a kind of a discrete, nested, let's say, build-up of jets with individual energy and bulk radiance factor. For instance, in this sketch, what I draw is a core which has a large gamma and a large energy, and then the nested cones have progressively lower velocity and lower energy. So if I am located at some viewing angle, of course, and time goes by, all these jets more or less independently decelerate. And so progressively, first I see the emission from, let's say, the green cone, which is more aligned to my line of sight. But as the red one and then the blue one at later times decelerate, so that bulk radiance factor decreases, so that the beaming 1 over gamma becomes equal to theta view, I start to see their emission. So I'm sorry, there is no correspondence in the plot with the colors, but you might think about the fact that we could think about this rise of the afterglow emission as the superposition of a green off-axis, the green part of the structure jet, then the red one of the structure jet, this dashed line, and finally the blue part of the structure jet. It's a very simplified representation, but gives you the basic idea of how it works. So the latest emission, which is not here, it's I will come to that in a moment. So when we reach the peak of this rising phase, we are basically seeing the innermost part of the jet, because this is the last one, having the larger bulk radiance factor, to become visible from a given viewing angle. In this picture, we can explain the low luminosity of the event of the gamma reversed, because basically this is due just to the because of the emission of the prompt phase along the line of sight. But I will come to this at the end of this first section. We can explain the appearance of the first afterglow, okay, when the gamma, let's say in this schematic view, the gamma of the green part decelerates enough as to be visible from the viewing angle I have. And we can explain the delay of the gravitational to the electromagnetic emission itself. We can most likely explain the shallow rise of the radio light curve. So the temporal evolution of the afterglow is, in my opinion, was the most compelling evidence that we are not dealing with a standard jet seen off axis, but rather with a uniform jet. So what is the physical motivation of a structured jet? Why jets in gamma reversed, and this argument is valid both for long and short, could have a structure? The reason is most likely related to the fact that the jet, which is launched by the central engine, has to propagate within a medium, which is either the envelope of the star or the ejecta, which were launched before the launch of the jet by the merger of the contact objects. So we have all the different types of ejecta, from the tidal to the wind ejecta. But in general, this is the medium, okay? So it's different. The word medium I'm using now, it's different from the external medium I discussed yesterday. That's the let's say, material, the interstellar material at large distances. Now I'm talking about material located within, let's say, for a long GRB, within 10 to the 11 centimeter from the central engine, or similar distances, 10 to the 12 centimeter for the merger of two compact objects. So the principle is that in general considerations, you have that if you imagine that the jet is propagating within this material, the jet develops a head of the jet, which is a region in which, due to the fast velocity of the jet with respect to the sound speed of the material, there is the development of a shock, basically a two-planar, you can imagine a two-planar shock, a forward shock and a reverse shock. The forward shock is shocking the material ahead of the jet, so the material of the ejecta of the neutron star, for instance. The reverse shock is shocking the material of the jet itself. And the end result is that the, let's say, capillary region, which is comprised between the forward and the reverse shock, is filled with the hot material shocked from the upstream material and from the material which is shocked by the reverse shock. Okay, so there are two directions of filling this region with hot material. So there is an overpressure within this slab here, which causes some material to be drawn apart and to, let's say, flow out of the jet, creating a kind of an envelope that contains the jet. And this is the cocoon material. This material is therefore filled with hot material which is shocked by the jet passage through the envelope of the star or the ejecta of the neutron star, and due to the high pressure inside, it is expanding. Okay, in this very schematic picture here describes let's say what I just said. Here you see the result of numerical simulations which show, for instance, with color code the density of the cocoon jet system and the enthalpy. You see that, for instance, the cocoon is filled with relatively energetic material, which decreases going to the edge of the cocoon. And there is the possibility, differently from this very schematic case, that the separation between the jet and the cocoon develops. So the wall of the jet, if you want, develops some instability, which is another way, not only the jet head, to have a mixing of the material. So the basic idea now, or the main question is, but what are the conditions that the jet should have in order to break out? Because you can imagine that let's say the fate of the jet depends on let's say the properties of the electromagnetic emission we see, whatever it is, the GRB or the afterglow, depends on the fate of the jet. If it is successful and so it breaks out of this material, or on the other side, if it is choked, so it fails to break out. Forgot to say, but it's obvious the structure of the jet that I discussed before is intimately then related to this process, because you see that there is an angular distribution in the jet and in the cocoon at a lower extent of the distribution of energy. So the breakout condition can be thought easily as a condition in which you basically balance the energy in the jet with the energy of the material which is in front of the jet. So the equation is here. This is the energy of the jet, and this part represents the energy of the ejecta of the material. Let's say, think about material distributed isotropically in front of the jet, times the portion of the material, okay, comprised within the jet, so right in front of the jet. This term here, modulus some factor. This energy is called the critical energy, so you can immediately understand that if the jet energy is larger than the energy of the material which is in front of it, the jet can travel through this material and break out. If on the other side the jet energy is smaller, the jet won't break out. So you basically take this equation, you take the ratio between the jet energy and the ejecta energy, which is represented on the y-axis. You have a scaling, which is like the opening angle of the jet square. Is the opening angle at the base of the jet, okay? Not the opening angle that the jet has at the end, which is the one that we discussed yesterday that we measure from the observation. As a function of the collimation of the jet at the base, you see that there is this dividing line. Everything below is not successful. While if the jet has enough material, larger than the ejecta material, you have that the jet is successfully breaking out. Of course, these two considerations, there are details here. You can look to the paper by Duffel and later references if you want to have more details. But in general, this condition also sets, let's say, the time scale for the breakout. The time scale, so the time needed for the jet to reach, if you want, the outer layer of the ejecta or of the envelope, in the case of a long gamma ray burst, depends basically on the energy the jet has. So the smaller is the energy of the jet with respect to the critical one, the later will be the breakout, because basically smaller will be the velocity with which the head of the jet travels across the material. So the bottom line here, the message is that the jet plus cocoon system is let's say, related to the jet energy and the opening angle of the jet at the base in first approximation, and the structure is imprinted by the interaction of the jet with the material. When I say structure here, I mean the global structure, not only the structure of the jet, but the structure of the system jet plus cocoon, because there is a bit of confusion, but in general, when we talk about structured jet, we comprise in this category either a jet which has only an angular structure without a cocoon, or a system in which you have some narrow jet, maybe also could be more or less uniform, so not structured, with the cocoon around. So it can be if you imagine that, can be kind of a smooth structure or a more discontinuous one, okay? And all the combination of the properties of these systems, jet and cocoon, or structure of the jet and cocoon, can lead you to different observational properties. Okay, so the question is now, what was...
we can see if there are questions.
Sure. Sorry, I can't hear you.
Yeah, it doesn't look like there are any. So just me, I would have one. So it's a bit puzzling, this fact that you have seen just one event with the gravitational wave counterpart, and it seems to be so different than anything, all the previous short GRBs that you have seen. So the question I had is, this idea of having a structured jet or a uniform with cocoon, etc., all this has been developed only after having seen 1708-17, or it was already, there was already the need to formulate these hypotheses before?
No, this hypothesis was formulated by far before, both that of the structured jet, but also on the nature of the structure, on the origin of the structure as due to the interaction of the jet with the medium, so the envelope of the star for the single massive star or the ejecta. However, it was almost impossible or very hard to find observational evidences in favor of this, because let's say the lucky point of 1708-17 is that being so close, it was possible to, let's say, monitor the emission, especially of the afterglow, over such a long time scale. The more distant GRBs with a similar off-axis angular position like 1708-17 would be too faint to be detected. And therefore, you know, there is this, let's say, angle bias that implies that if we go to larger distances, so I'm thinking about cosmological gamma ray burst, redshift 0.51, okay, the sources we pick up from the population are those in which the jet is more aligned with the line of sight. And in that case, probing the, let's say, structure of the jet, of the presence of the structure of the jet is a challenge, because you cannot distinguish that from a uniform jet, because you are just seeing basically the core, even if structure of the jet, which is not that much dissimilar from a uniform jet. Okay, but the theory, I would say, was much developed before this, and there were some attempts also to try to use the observations available to say something. They were not as conclusive as in the case of 1708-17. Even though also in the case of 1708-17, as you will hear now, I mean, we have strong indications of the existence of a structured jet, but probably, you know, there was not a debate, but a discussion for these two competing models, because many of the observational properties I presented and I present now could be explained also without the emergence of a jet. So in the case in which you have a failed jet, but just a cocoon emission.
Okay.
Up until a certain point, we will see.
So there is also a question in the chat. Maybe Ilsan, you want to ask it?
Yes.
Please.
Might be a naive question, but I'm wondering, for all these nested jet in the structured jet structures, are there time evolution of gamma factors the same for all the nested jet, or could be the jet have their own, you know, different time evolution of gamma factors? So the later the beaming angles actually could be overlapped or interact.
Sorry, I didn't get clearly the question. I couldn't hear properly.
Yeah.
Can you formulate it, please?
Yeah, I'm sorry. Basically, I was wondering, each jet have their own time evolution of gamma factor, right? So
okay.
My question is, are these the jets in the nested jet, will they have all the same, you know, time evolution of gamma factors, or each jet have a slightly different time evolution?
Okay, no, well, this scheme or picture I'm presenting is an oversimplified one. In reality, it is very likely and possible and very likely that the evolution of the structured jet is something which is not completely independent from angle to angle, okay? Because maybe at the very beginning, when the most of the jet is expanding at ultra-relativistic speed, it can maintain a kind of independence, but as time goes by, it tends to lose, let's say, collimation, even the individual nested jets, and there could be mixing even of material of the different regions. So the way I'm using to present this, let's say, case is like an oversimplified case, and in general, to understand the picture is sufficient to think about, like in this drawing here, that we have an independent evolution of the gamma factor. This is done, and I did it in order to let you think about the emission you see as the superposition of many independent jets that evolves independently. But in reality, this is not the case. The surface, let's say the evolution of the jet is treated self-consistently and uniformly with within the total opening angle of the jet, which can be several degrees up to 90 degrees. Okay, with its structure of both the Balken's factor and the energetic. And then the other point is that if you just think about the deceleration that we discussed yesterday, one of the key parameters is the external, of course, the energy of the jet and the external density of the medium, okay? So there could be situations in which you have, for instance, also a distribution of the external medium, which is not perfectly uniform in angular coordinate. And this could imprint a different, let's say, temporal evolution and deceleration pattern to different parts of the jet. So there could be also these effects to take into account. But at first order, to understand in general the picture, let's say that at least at very early, relatively early times, it is sufficient can be sufficient to treat the jet as a discretized series of jets with a prescription with a structure like the one I showed before, the power law of the Gaussian one, discretized over a length scale which is small enough in order to assume reasonably that they evolve independently. Numerical simulation, as you see in this plot here, for instance, of course, describe much better the time evolution of the whole structure, which, as you see, is not independent. Here you see there are mixing of the jet, even in the of course, in the at smaller angles at later times. This is a case of a successful jet.
I see. Thank you very much.
Okay, so there is another question by Eric.
Yes, and it's exactly in the following of what you just said, Giancarlo.
Yes,
you know, when I look at those simulations that we have now here in front of us, I can understand that the model you've been presenting today, the jet model that you've been presenting today and yesterday, can capture a lot of the physics that we see. But I see also turbulence, right? I think there is turbulent flow, and I guess that this is not part of the model you have so far. Am I right? And yeah, and do you think that the turbulence may have a real contribution in the jet, and therefore a signature that we don't capture in the signal that we observe today? I mean, the gamma ray signal.
Yes, so you are perfectly right. I am using this oversimplified, say, model. What simulation says is much more complicated. For instance, in the case of the cocoon or failed jet here that I'm showing, you see that mixing and turbulence can play a much more relevant role than probably what happens in the case of a successful jet, because in the case of a successful jet, let's say that models, I think, don't know exactly the number, but I would say a factor of a few, you can still treat the problem with a narrow, fast and very energetic core and some tails. In the case of a cocoon, you have a very complex stratification, for instance, in the energy and velocity in the radial direction, which, for instance, here I propose as a very simplified picture, which is not really the case, and can indeed, I think, in the cocoon case, have imprints on the observed light curve, at least I would say in the very early phases, because it is in the very early phases that you see the fastest material breaking out, and then you see the brighter emission due to the short breakout. And probably in that case, in the case of a chalk jet, you can have some indication of the let's say fine grain distribution of the energy and velocity within the outflow, which is not only radial, but can be also angular, like you see here, with more structures. Not, to my knowledge, with the observations we have now, even for the case of 170817. It is only based on theoretical simulations, not yet proved. I don't know if future observations may be will have some signature, especially in the very early phases. In the case it is a shock jet, so relatively low luminosity event of this peculiar structure that you have here, for instance. This is in this plot you see the velocity, and in this case you have the energy. Okay, here is the velocity, here is the energy.
Can I add a quick question?
Yes, sure.
Is part of the variability that we see in the gamma ray signal today could be related to the turbulence in the flow here?
Well, let's say that specifically this case has not a large variability. So if you think about the variability like the one we discussed yesterday, typical of cosmological gamma ray burst. So I don't remember the value, but to my knowledge, the variability of 170817, the GRB, is not large. So if you think about instead the variability typically observed in short GRBs, cosmological one, or long GRBs, I think that kind of variability is most likely ascribed to the variability of the central engine. So in the way power is in a way discretized, for instance, through accretion. I think that the variability of these structures that we see either here or here is not probably resolved or smeared out by the fact that you capture within your sampling time scale the integral of these effects, which are very tiny, and therefore is washed out by the integration time.
Right. So you're saying that if there is a
Please.
Sorry, if there is a trace, it's more like it's not in the prompt, definitely. The timescale are not matching. But it could be later on in the afterglow that we could
I guess so, not maybe in terms of variability, but in signatures of the fact that you have some kind of discretized distribution of the energy and velocity in the early afterglow.
Okay, thank you.
I think, I mean, I'm just guessing more or less based on intuition rather than having a clear demonstration.
Okay, so there's doesn't seem to be any other question. So if you want to proceed. Okay.
So yes, so thank you for this question. So they allow me to, let's say, warn about the oversimplified picture I'm giving. So the basic question for what I said before is, did a successful jet or was a short jet the case of 170817? This question remained for quite a long time. So after 100 days, with only this piece of evidence, there was much of a discussion because the, let's say, rising of the afterglow is consistent with both these scenarios. In fact, if you think about a shock jet, you can imagine that, as you see here, of course, approximating that, you can think that even though the jet doesn't break out, the jet head deposits most of its energy within the ejecta, and it imprints, at least out to an angular scale, which can be of the order of 60 degrees, so very large. It imprints an energy and velocity distribution, which can be thought as a kind of a stratification like this, where you have the front part of the ejecta, which is loaded with less energy but is faster, and the rear part, which is more energetic and traveling at a lower relativistic speed. So this implies that the emission that we see is produced when this system breaks out, becomes transparent, and therefore there is a kind of progressive superposition in the light curve we see of the emission of this, let's say, stratified material, which somehow peaks and produces the overall envelope of the rising afterglow light curve that we observe. The key difference, or the profound difference between these two possibilities, which are not excluded, I mean, while both valid, is realizing the fact that in the case of a jet, let's say the rise of the emission is produced by a combination of a geometric and relativistic effect, okay, beaming becoming equal to the viewing angle. In the case of a chalk jet, the viewing angle is almost, let's say, influent, and instead it is mostly a dynamical effect, because it's due to the expansion, roughly, that the light is released because of the material becoming transparent. So this was the question, and as you know, people went on collecting the observations, the observational data, up to the time when the emission peaked. And even later, okay, the peak was detected at around 150 days. And again, with all this information, so with one, maybe I think the best short gamma reversed afterglow ever sampled at different frequencies, from the radio through the optical and X-ray, and having such a complete view of the light curve rising, peaking, and decaying, it was still not possible to disentangle which of these two scenarios is the case. Here I propose to you realistic fit to these data sets that you see here. These are the light curves in different bands, as you read from the legend, with two models which are perfectly consistent. Here you see with the dashed line the chalked case with these parameters, and you see with the solid line the Gaussian structure jet with these parameters here. And if you look to the values of the parameters, they are reasonable, because for a Gaussian jet structure, we have an energy of the core, which is that of a typical cosmological gamma reverse jets. We have a bulk arrest factor, which is typical, like the one that we discussed yesterday. The opening angle of the core itself is of a few degrees, as those that we measure for a few short GRBs and for a larger number of long ones. The ISM external density is relatively low, but can be, I mean, justified. And on the other side, despite we don't have, let's say, many cases or no cases to compare with, however, the, let's say, energy and possible stratification of the energy as a function of momentum is what at least consistent with numerical simulations that were performed even before the detection of this event. So what are the, let's say, observations that can help to disentangle this situation? I'm showing those that were collected. Of course, these observations, some of these worked for this event, other not, but are, however, killing observation for any other possible future event similar to this one. The first one was related to polarization. Polarization measurement of the emission, let's say, depends on several factors. There is a first factor that determines the linear polarized fraction of the emission, which is produced, for instance, by a jet, which emits by synchrotron emission during the afterglow phase. And depends basically on the asymmetry of the region which is producing the light we see. So in general, you can think very naively that for a more isotropic emitting surface, like for instance in the case, or wide angle emitting surface, like in the case of the chalk jet, the polarized fraction of the light should be quite low. On the other side, if you have a jet, here people thought about the core of the jet, of course, you should see, because of the asymmetry of the, let's say, region with respect to the line of sight, you should see a quite large polarized fraction of the light, which, by the way, depends on the time. The reason being the fact that you can think that this line is thought for the inner core of the jet, which is, or the innermost part of the jets, which, of course, are low at early times, and also their polarized fraction is low, and then it increases when you start to see much clearer their emission. Polarization was measured for 1708-17 through an observation which was around the peak, just past the peak of the light curve, and the result was an upper limit at a 90% confidence level, less than 12%, which is this point here. If you compare with the models going from a, let's say, shock jet to a structured jet, apparently this upper limit seems to exclude the fact that we have a situation like this, and seems to be more consistent with a shock jet, of course. However, there are some complications, because the measurement of polarization is challenging. The source should be bright enough, but from a theoretical point of view, the polarized signal can be strongly dependent on the orientation of the, let's say, component of the magnetic field parallel and perpendicular to the shock front, which is producing the photons. Okay, so as you see in this plot, by changing the parameter B, which measure the intensity of the magnetic field in the plane perpendicular to the shock with respect to the parallel one, you can basically, also in the case of a structured jet, you can lower substantially the polarized emission by changing, especially increasing the fraction of the magnetic field, let's say, component perpendicular to the jet. So this let's say, observation was important, but was not conclusive in distinguishing these two emission components. The best possibility is instead to rely on imaging, because from very simple geometrical consideration, you can understand that if you have a structured jet, in general a jet oriented off axis with respect to the line of sight, if you're able to monitor the position of the source with high accuracy, you could in principle see the proper motion of the source in the plane of the sky. If instead you have something which is much more isotropic, nearly isotropic, whatever direction you look to this source, you should just see an increase of its size as a function of time because of the expansion of the source itself. It's a bit more complicated, of course, because you have to cope with the fact that light is emitted by different parts of the jets as a function of time. But I think that this plot here encodes more or less this principle. Here you see a case of a simulation performed by Gilles and Granot, and then there are other works by Drake, 2018, where they simulate the image that one should see in the plane of the sky with real, let's say, coordinates. Scales here are milliarc-second. If you observe both these scenarios, oversimplified here, so the case of a structured jet or a cocoon, at an angle of about 30 degrees. And as you see, in the case of a structured jet, what they see, the jet is moving in this direction, okay, so leftward in the slide. This point is the center of the explosion, and they simulate the jet as 100 days, so slightly before, if you want, for comparison to 1708-17, the peak, 200 days, 400 days, and 800 days. You see that the effect is that the centroid of the light, also the blob that one should see, for instance, in radio images, is moving apart from the center of the explosion up to about 400 days. And then there is a counterintuitive effect, because you see the centroid, which is represented by the yellow point, seems to go back. The reason being the fact that the jet is not unique. I mean, the jet in GLBs, I forgot to say, is bipolar. So at some point, you start to see the emission of the counterjet, which becomes all non-relativistic, okay? And since the yellow point is the average of the surface brightness distribution in the image, the average, of course, is balanced by the forward jet, the one which is more co-aligned with the line of sight, and the rear one, the one expanding in the other direction. In the case of a uniform, of a chalk jet, on the other side, you have that more or less there is not much displacement of the centroid of the emission, okay? There can be some displacement, but is not as much as in the case of a chalk jet. Look at the similar epochs. And instead, the overall, let's say, outcome is that the source surface brightness somehow becomes larger and larger. You can appreciate that also by the error bar associated to the average distribution in the y direction here of the light. So this was the theoretical predictions that we had, and a campaign performed by the US colleagues employed the VLBA, so employed the largest radio telescope interferometers in the US. So they joined the VLA, the VLBA, which is a network of radio telescope distributed from south to north, and the Green Band telescope, which is one of the most performing among this network of the VLBA. And they observed the source in 4 epochs. These epochs were distributed between 70 days and more than 200 days. They then joined in pairs this observation in order to increase the significance, and they obtained 2 images on day 17 from the gravitational wave event and day 230, which are represented in these 2 pictures here. And they obtained this fantastic result, which is represented in this plot here, because they could measure that the source position changed by 2.7 milliarc second in, what is that, 160 days roughly. So by measuring this displacement having the time of the 2 epochs, it is possible to derive the apparent speed at which the source expanded, moved in the plane of the sky, which is a superluminal value of the speed, because it turns out in this case to be apparent beta equal 4, okay? It is superluminal because it's an apparent effect due to the fact that the source is indeed moving with relativistic speed, but due to the, let's say, misalignment of the source with respect to the line of sight, but not that much, we are not looking to the source perfectly at 90 degrees, what we measure is a beta which is proportional roughly to approximately equal gamma. And therefore, it can be shown that the measurement of this apparent speed, the reverse of 1 over gamma, so it's proportional to the displacement of the line of sight with respect to the jet opening angle. Sorry, there is a typo. This is theta jet minus theta view modulus of, okay? And so it turns out that this was the first evidence that in order to justify such a large displacement, we have to think about a source which is moving in the plane of sky at relativistic speed, and a source which, let's say, is quite compact. It's the other point that is implied by these, let's say, different cases, because it is true that in the case of the structured jet, there is the movement of the source, but as you see, up to relatively large days, you have that the source remains compact. Whereas in the case of a chalk jet, you have almost no displacement, approximating, but you have an increase of the source. So the source becomes larger and larger. So this was the first proof, the fact that the source moved in the plane of the sky. and these allow to derive the orientation angle, and also to probe that a relativistic jet, or at least the core of the jet, because this observation, the last one, the 200 days, is sampling the emission from the core of the jet, was launched by the binary intrastar system. We wanted to have the other piece of the information because, as you can see in these images, while you can probe very well, because of the very high precision astrometry, the position of the centroid of the emission, you cannot set a very strong constraint on the size of the source, because there is this elongated pattern because of the, let's say, configuration and position of the interferometer of the antennas on the ground, and the position relative to the position of the source in the sky. And so we, as yesterday was saying, Eric was saying in the introduction, we performed another observational campaign in the radio band in order to, let's say, try to constrain the size of the source. Of course, this was a challenge because we performed this observation 200 days after the explosion of the burst. This was at the peak, more or less, of the emission. So it was in a favorable condition, but the source was, on the one side, dim for, let's say, the apparatus we could employ. And on the other side, most of the radio telescopes that we used were in the northern hemisphere, while the source was in the southern observable best from the southern one. And so that means that these telescopes had to observe the source at a very low elevation, which, let's say, in the radio band makes several complications related to disturbances, interferences, and the difficulty of, let's say, correcting for the disturbance effects related to the transmission of the atmosphere, whose column density is larger. So we performed these observations, however, employing 30 radio telescopes, which 32 radio telescopes, which were distributed from Australia to the Hawaii, and of course observed the source thanks to the rotation of the Earth at different times for a small amount of time each one. But the goal and then let's say the effectiveness of this kind of observation is the capability of correlate the observation of individual telescopes all together and derive an image like this one, which the first time we saw it, we were really, really excited. We said, "Ooh, Eureka, the source is visible, is detected." The detection is at 5 sigma. As you see, the peak brightness is 42 microjansky. It's really at the extreme, let's say, it's quite dim, okay? And this required that the analysis of the data was in a way much more sophisticated in order to assess the significance of the source and the size of the source with robust arguments. Of course, our observations was in between in terms of days between the two observations I showed you before, and this was a way to probe and to add a third point to the proper motion. So these are the two points obtained with the HSA by Muley, and this is our detection. This is the source in the reconstructed image. Let's say that our result is not, however, the proper motion, but the fact that we can constrain the source size to be smaller than 2.5 milliardsecond. And this result, in order to understand it, we can play a very simple game. So we can build a model for a structured jet and its competitor, let's say, short jet model. We build up the plane, the image that we expect in the radio band. We fold that with the noise of the real radio images, and we compare, in this case by eye, but then there are, of course, quantitative methods to perform this comparison. We compare the, let's say, mock images with the real one, like a clue who is which is the real one. And of course, you see that the successful jet case, so the structured jet case, is the one that produces a simulated image which is more consistent with the real one. The reason being the fact that, as I said, I tried to explain you before, in the case of a chopped jet, the size expansion is so much that basically the source becomes so large and distributes its brightness over a large area that with the resolution we have with the radio telescope, it becomes resolved. When it becomes resolved, given the fact that it is very dim, it would be undetected. So you see that in these two images, it's not only the shape of the source, but the fact that the source is almost not detected because its emission is distributed over a wide, let's say, region, and it would have been not even detected and not as compact as instead it is in the real case. So what is the outcome of these two observations? So combined with the evidence of the rise of the afterglow, now if we fit together the rise of the afterglow, so and the peak of the afterglow, so all the light curves I showed you before, the displacement of the source in the plane of the sky, the proper motion, and the size constraint, so the condition that the source should not become larger than the size we measure at 230 days, the apparent image of the source, we can derive a constraint on the structure of the jet. And here I show you the results we obtained in our work, which is represented by the red line with its uncertainty, the pink region, compared with other structures that were obtained with either one of these three constraints that I described. For instance, just fitting the light curve of the afterglow, or just the proper motion and the afterglow together. So we derive that let's say these three pieces of observations could be well described by a structured jet, whose structure in this case is described by a power law, and we found results for the core energy of the jet and the jet core opening angle, which is consistent with the values I showed you before. So it's 10 to the 52, the kinetic energy of the core, 3.4 the opening angle of the core. We found that the core opening angle for the energy, kinetic energy, and the core opening angle for the gamma factor are similar. We found a slightly steeper slope for the decay of the power law for the bicurrence factor with respect to the energy. And we could constrain the viewing angle of the observer, which turns out to be approximately 20 degrees. So if you want, in the structure is, let's say, located more or less here, okay, where there is this point. The comparison with the other observations, with the other results, with the other structures, so that in general there is a good match, consistency, but of course the power of combining these three observations excludes at least some of these structures, which are based on a less number of constraints. Okay, so I think this is the end of the part describing the fact that we observed a relativistic structured jet emerging from the neutron star mergers. If you want, now we can let me see. Okay, how much time do I have, Chiara? So
like yesterday, you have until midday.
Okay.
In principle, so allowing for questions, but since we ask questions while you're teaching, so I think you can teach up to midday.
Okay, no, probably today I will be faster so we can get more questions or discussions. But so if you allow me, I would just take 2 more minutes to conclude this first part before moving to the kilonova.
Yes, absolutely.
Okay, so now the important point is that we think we have understood what was the structure of the jet emerging in 1708-17. But now, what happens if we take this burst and we think in a kind of a universal approach of the fact that the jet structure is something common to other bursts? And so the question is, or the curiosity, but what if our friend were looking to the jet along the axis? What would have he or she observed? Of course, the question is twofold because it pertains to the prompt emission and to the afterglow emission. Let's start with the afterglow emission, which is the one which behaves better. The afterglow emission is shown here. So here you see the exercise. This is the, let's say, light curve, just at X-rays. Here it is in the radio band, and this is in the optical. You see they are almost the same, of 1708-17 as observed, okay, of the afterglow. So if you now think about taking the same structure and moving the observer more and more on axis, you basically see that when you reach the border of the core with the viewing angle, you should see a light curve like this one, the dashed line. And when you are within the core, you should see a light curve like this one, the solid one. These let's say light curves here, you see in the X-ray, and these points here are a collection of observations of cosmological gamma ray burst light curves, like the gray points I showed you in the first slides. So for the population of short GRBs, what this demonstrates is that with the given structure that we derive by modeling all the informations we have from the light curve and the radio imaging, if this burst is common, this structure is common to other GRBs, 1708-17, if observed within the core, would have appeared as a normal afterglow, both in the X-ray, in the radio, and in the optical. The somehow less or more intriguing case instead regards the prompt emission, because now the exercise can be done in different ways, but I think the most intuitive is probably this one. I showed you at the beginning of this lecture that the way of discussing the prompt emission of 1708-17 is using this correlation between the peak prompt energy and the total isotropic energy of the prompt emission. So these are cosmological short GRBs. And what we tried to do here was to, let's say, observing the structure of the structured jet of 1708-17 from progressively faster, larger angles. And therefore, what happens is that with the uncertainty in the structure we have, is that the, let's say, off-axis view of 1708-17, if its core, as it is, appears similar to normal GRBs in terms of kinetic energy, opening angle, and bulk currents factor, it should lie within this region. You see that it is marginally consistent with this argument. So if you want to reverse the, use the argument in two ways. So for the prompt, I reverse the way, okay? You can work also the other side. You take 1708-17 and you go to see where, where it would lie if observed on axis, and it would be somehow apart from the distribution of the other bursts, okay? And so there is this marginal consistency, which is given the viewing angle. You see these plots show for the viewing angle that we derive from the afterglow and imaging of the radio observations. The burst is maybe a bit more consistent with the peak energy of cosmological GRBs, but the major issue is on the isotropic energy, which is really at the border. And this is a question. Possible answer is that the description we have from the modeling of the afterglow of the structure of the jet is missing one possible element, which in the afterglow is maybe not that relevant, but instead is relevant in the prompt emission. And the fact that in doing this exercise here, we are assuming that in the prompt, you remember the bulk currents factor is constant and doesn't change with time, is constant, but is structured with the angle. But the radiation we see depends also on the efficiency of dissipating the kinetic energy that the outflow has acquired at the end of the acceleration during the coasting phase, you remember yesterday. And this efficiency in this exercise is assumed to be constant, but it might be well also structured for some reasons that is related to the dissipation mechanism. Okay, so it's an hypothesis, but it could be a way, for instance, to solve, let's say, this slight inconsistency or position of the prompt emission of 1708-17 with respect to, let's say, the other bursts, if interpreted like having a structured jet similar to the one of 1708-17. So the summary slide of this first part is the following. While we have a nice, let's say, interpretation, I would say, of the, and also compelling evidences of the fact that the afterglow emission is likely described by structured jet, with a structure which has a small core and some wings of material moving at considerably lower velocity, bulk velocity, and with lower energy, because the structure is steep, as I showed you in the previous slides. The point is that probably we need still to think or to understand better what is the origin of the prompt emission, because at an angle which is located at, let's say, 20 degrees, like in this case, it could be that, for instance, the prompt emission is dominated by the cocoon shock breakout. Having a structured jet doesn't exclude the possibility of having a cocoon, because, as I showed you, the same, let's say, imprint of the structure of the jet due to the passage within the ejecta also creates the cocoon. So the two elements are not mutually exclusive, okay? And so it could be that the emission we see for the prompt is somehow dominated or due to the shock breakout of the cocoon, while the afterglow emission is dominated by the structured jet. The reason being the fact that there are different expectations. In the case of a cocoon, it's okay having a low energy for the prompt emission. We should expect a relatively small variability during the prompt, and it can explain the hard-to-solve spectral evolution, and also the delay between the gravitational wave and the electromagnetic emission. This is something I forgot to say. In that case, the delay is simply due to the, let's say, to the time needed for the cocoon to reach its transparency, which is basically its breakout radius, which is represented here by this equation. The time of the breakout of the cocoon is of the order of 1 second for typical energetics of the temperature, typical energetics and temperature of the material itself. On the other side, the structured jet wings could explain a higher variability of the prompt, which is not observed, can explain the delay, but at the expense of having a structure not only in the energy and bulk radiance factor, but maybe also in the efficiency, which means that at large angles, at 20 degrees in this case, to explain the prompt emission, we should have somehow lower efficiency with respect to the prompt one. And I stop here.
Thank you. There are a couple of questions, so let's start with Raphael.
Hello, Giancarlo. Thank you so much. Hi. Thank you so much for this fascinating description of this historic event. There was one thing that you didn't mention, is where does the remaining uncertainty in the fitting of the afterglow and of the image remain. So if you allow me, I will share in the chat one figure from one of the papers where you deduce the constraint on the jet, and I lost it. So
do you want to share the screen, Raphael? Do you prefer to share the screen?
Well,
I don't know
if that's allowed by Chiara, sure.
Yeah, absolutely. So Giancarlo will have to stop sharing and then.
Great.
Okay.
So wait.
Sorry for the technicalities.
No. It's a discussion and.
Whoops. Okay, so please correct me if I'm wrong, Giancarlo, but what I'm showing here is the posterior sampling of the different light curves, which correspond to the uncertainty that you obtain in the structure jet after the fitting of the light curve and the imagery as you described. And it seems to me that the remaining uncertainty is in the very, very early times. However, I expect that in this very early times, the emission of the afterglow is still dominated by the material which is on axis. So this is not on axis, on our line of sight. So this is before the onset of the slowly increasing phase, and therefore in this region you should expect the behavior in T to the 3, which is valid for a single ring if you forget about all the structure. And therefore I was wondering how come there is so much uncertainty here, whereas in this phase the structure of the jet does not contribute to the light curve.
Yes, so you're right. In this, more or less in what we said today, in this picture, what you should see is that the core of the jet is dominating the emission here, okay? Because you see the core at the peak of this light curve. Everything we see before the core is the emission of the afterglow produced by, let's say, the wings of the jet. And let's say in this region here, very early phases, I don't know how much let's say, combination of let's say, the wings of the jet. I mean, the dependence of these curves here is related to factors which are not under control in this modeling, such as, for instance, the total opening angle of the structure of the jet, because either you can think about the structure extending to 90 degrees, or you can think about a structure which extends to some limiting angle. I don't remember. Probably here we consider something like 60 degrees in this case, and it then depends strongly on this, I think, and I don't know what else could be.
Yes, but when you look at the afterglow in the early phases. So for example here, so this is typical modeling, and you see that there are 3 phases. There's this phase, which is of course when the core was revealed. There's this phase, which is the slowly increasing phase, where you have progressively the whole structure which contributes, and then you have this phase, which is when you are dominated only by the line of sight material, and here it should be T to 3. Do you agree? That it should always be right. T to the 3 here.
Yes, T to the 3.
And is this phase what's corresponding to the uncertainty here, or?
I think so, but the problem is that here in our plot, what we're doing, we are sampling the posterior distribution, and therefore we have several of these possible contributions. Probably the less realistic ones, I cannot use the mouse, are those which you see produce this slight bump here. Whereas in the plot you show, I guess, I don't know the plot where it's coming from, but I guess this is for a single structure. So like in my plot where I showed you the comparison of the structure we derive with the others, indeed, what we do in order to make all these lines is by resampling the possible combination of all the gamma and kinetic energy within the posterior distribution, whereas probably in your case, you're showing a single combination yes. of gamma and the energy.
Okay. Yeah, this is one case. Okay. So you think that the overall structure also influences the early phase? This is why
yes,
explains why it is.
As you say, I mean, the very, very early phases, in the very simplified case in which you assume a single structure, is basically its slope is dominated basically by the emission along your line of sight. So it just depends on the patch of the jet with its kinetic energy, with its Poincaré factor along the line of sight. And it should be standard as a rise modulus defect that, well, the way I think that it depends also on the way you discretize the jet, because the Poincaré factor is very low. So you can have along your line of sight, but you have to integrate over the parts which are nearby your line of sight, which can contribute. And this maybe can make a slight departure from the very simplified, let's say, law, which is t to the third, as if, which I think is valid as long as you are assuming that you are dominated by the emission along your line of sight because of a large enough Lorentz factor that the emission aside is not contaminating the light curve you see.
Okay.
Yeah, it's much clearer. Thank you. Thank you so much.
Thank you.
There is another question by Susanna.
Yes, thanks. I comment also this point because from the plots that are not visible anymore, the one that Raphael showed, in fact, the time scales are not yet those of, if the time scale is the same in days, the time scale of the Giancarlo's plot is not yet the one at extremely early time when we are dominated to 10 to the 3. To a power of, you see? I mean, it's just 10 days there. So you are not at the very, very early stages where you say that you are dominated only by the your line of sight. So
right, absolutely. Yeah, I hadn't noticed that, but thanks for pointing it out. Absolutely, yeah.
Yeah. So my question was, Giancarlo, on your plot where you show the discrepancies for the prompt emission. I think the last but one slide.
I can.
Yeah, if you can share is better. Sorry.
Sorry. Do you see?
Yes. So two slides before another one. Yes, this one. So sorry, I was confused. So then I couldn't follow exactly what you were saying exactly. So what do you mean in the left plot 1708-17 as observed?
Though I mean the properties of 1708-17 observed at the off-axis angle of about 20 degrees.
So I'm not sure I understand the plot, because I was thinking of a plot where you showed what we had from on-axis gamma ray burst, and then a point representing the on-axis view of 1708-17. So starting from what we observed and the modeling, putting it on axis, what we would have seen.
No, it's the reverse, in fact. So I wasn't clear in this. So this exercise that you see for the afterglow and the prompt is the opposite. For the afterglow, is exactly what you said. So we take 1708-17 and we move the observer towards the axis, and we see how the light curve changes.
Yeah.
Here we do the opposite exercise. So the plot and the points are real. So these are normal short GRBs. This is the position in the peak energy, isotropic energy plane of 1708-17 as it was observed, which is the same for the black points. These are the observed, I mean, rest frame, but as observed properties of these short GRBs. And here the exercise is saying, if all these short GRBs had a structured jet similar to that of 1708-17, they basically constrain with their observed energy, assuming that they are observed basically on axis within the core. They give you, let's say, the normalization of the energy in the core and the Poincaré factor that you assume similar to that of 1708-17. Assuming the same structure, we see what they would appear like if we observed them at larger viewing angles. So I make you an example to make it clear. We take this burst and we say, okay, if it had the same structure of 170817, given the fact that we observe an energy which is 10 to the 51, we say then that the core energy is 10 to the 52, kinetic 1, and moving the viewing angle, okay, moving the observer, it would move along this line, or taking into account the uncertainty, should lie within this region, 68% and 90% confidence, okay? And so, I mean, is 170817 compatible with being like the other, let's say, short GRBs, assuming that the jet is universal, just because seen at large angles? The answer is yes, but a bit at the border, okay? Doesn't lie here, for instance.
Yeah, so in this sense, this can be explained because also the explanation on having the jet plus the cocoon. I don't understand, okay. I don't fully understand why. Okay, I understand that if you add the cocoon, you will add a kind of peak flux, so you combine both things. But why shouldn't it see, even on axis, I would have a cocoon?
Yes, but in that case, you are totally dominated by, in what you see, by the emission of the core of the jet. It's much larger. It's 10 to the 52 compared to 10 to the 47.
Yeah, so what I'm saying is that when you do the red line, actually you're just taking into account the jet, and you would not know how to correct for a cocoon, let's say.
No, in this exercise, it's only for structured jet without the cocoon. The argument for the cocoon, as you see, or in general for some modification in the structure of the jet, which probably is not in the energy and bulk balance factor, but could be in some other parameter. There are works by Yoka, for instance, that do this, and also maybe something by Nakar, 2018-19. All the papers are distributed in the last 3 years. So the point is that in order, if you want to reconcile this discrepancy, the main action you have to do is somehow to change the peak energy, okay, along this, if you want to move it vertically. So it's like 170817 had a slightly harder, let's say, peak energy, harder emission spectrum. That's why I was mentioning the efficiency, which it's tricky because it should affect, let's say, the energy distribution of the emission rather than not that much, at least the radiated energy as a total, because otherwise you would move it also horizontally.
Yeah, and just to conclude my common question, sorry, again on the effect on having a contribution additional to the jet, shouldn't this change also the afterglow emission? This cocoon would also emit some way in other frequencies, or not? It will encounter the stellar medium as well.
Yes, this is possible. I would say, I mean, it depends. You can still have some contribution. I think it would become, with the cocoon and the structured jet case, probably for the afterglow. I think in general the argument is that you don't really need.
No, you don't need it. But if you put it in one ingredient, you should have some effects in the afterglow as well. Maybe negligible, I don't know, but
I think it could make some differences in the early phases, because when as also Raphael was showing, in the very early phases, when you are only dominated by the part of the jet, let's say at large angles, or by the cocoon, if they are independent, maybe you can have some signature of a difference with respect to a structured jet only, like this light curve here. So maybe there could be some enhancement, possibly, of the afterglow emission in the very early stages, because they are somehow independent in a way, no? of course, they are related in the sense that probably the energy that you push in the cocoon is related to the energy you had in the jet at the base. But then when the cocoon breaks out and the energy it releases, it's related to the energy of the cocoon independently from the jet. So it's like having, I guess, a possible emission component which can become more relevant when the jet emission is less relevant. So I guess in this phase is here.
Okay, thank you. Sorry for using so much.
No, thank you, Susanna. I mean, it's good. I mean, I think first of all, you allowed me to explain better these pictures, which are not really intuitive, and thank you.
Okay, so we have another question by Il-Sang.
Yes, thank you. I would like to ask a question regarding the picture on the right-hand side, the afterglow emission. So you compare the GRB, the 170817, with respect to the overall populations of the short gamma ray bursts, and you demonstrated that if you change your viewing angle and matches to the jet, then this observation getting closer and closer to the general, the trends of the ensemble of this short GRB. But I was wondering, does that really mean that on the ensemble of the GRBs usually have the perfect match between viewing angles and the jet?
So they usually have?
So does that mean that the short GRB populations have the viewing angle matches the jet?
Yes. Let's say if you want another way of looking to this is that the short GRBs that we have observed so far are, I would say, structure jet observed close to the axis, basically within the core, whatever it is. It's opening angle, but it's like, if you look here, let's say this is the viewing angle of 170817, okay, and most of the short GRBs we know about have been observed with an opening angle which is sampling this part of the bulk coherence factor and this part of the energy, so within the core. This is the opening angle of the core, okay, 3.5 degrees. So yes, and this is, I mean, intuitively, this is, let's say, understood for the fact that the light curve, as you see, for all these bursts, is decaying as a function of time, as that expect for an afterglow seen within its opening angle. And their luminosity and energy is large, okay? If these bursts were observed, so the point here is that if these bursts were observed at large angles, they would have appeared with an afterglow like this, and with a luminosity and hardness which is quite low. So this argument at the end says that in general 170817 appears as a, let's say, strange event for what concern its strange event, not common event for what concern its prompt emission energetics and hardness, and for what concern the evolution of its afterglow light curve. But overall, it can be made consistent with the other bursts under the assumption, under the condition that seems to be met by the observations of having such a jet structure with the viewing angle and the beaming angle effects.
Okay, thank you very much.
Thank you.
Okay, so I'm not sure how you want to proceed now. Do you want to have a short break, or maybe there is not enough time, you want to go straight to the kilonova part?
I think I need at least 1 minute of a break.
Absolutely, yes. It's you decide.
Okay, no, it's
So-
required. So
Okay, so shall we reconvene like in 5 minutes?
even less if you want. We can. Okay, let's do
It's
5.
up to you.
No, the second part, I think it's probably not that long. So
Okay.
I don't know. Okay,
Okay,
5
so
minutes. Let's take 5, just 5. Okay,
just 5 minutes. Okay.
thank you.
Giancarlo, ti rompo le balle un altro secondo. Se metti i fermi dentro la figura lì del prompt. Yes, I will speak in English anyway. If you put the Fermi GRB in that prompt figure, would you cover a bit the parameter space of 170817? You're muted.
Can you hear me?
Yes, yes.
Yes. So no, this plot, Susanna, is in the this one. I think you mean is in the rest frame. So for the
Yeah, okay, you need redshift. Yeah, fine. Yeah,
majority, we don't have the redshift.
But if I can add, I'm sure you know this paper by von Kenlin in 2018, I think, where they searched the Fermi database for gamma ray bursts similar to 170817. So most of them don't have redshift, so it's the same answer as Giancarlo. However, they do have spectral properties which are interesting and which are similar to 170817.
Yes, you're right. Even though I had a slide which I skipped because of time. In fact, this is a very nice question. I mean, from just the prompt emission, if we do search for GRBs with similar observed properties like 170817, what do we find? There was this search by von Klein and in the Fermi sample. They end up with this sample of, let's say, relatively soft GRBs and very dim events. For most of them, they don't have redshift. However, there is a paper by
Matsumoto,
right?
where they study the shock breakout possibility for these
yes, correct. So they apply the compactness argument, refined one, with taking into account all the sources of the compactness and the interplay that the bulk currents factor has on the compactness. And if I remember correctly, their conclusion is that given the fact that there is no redshift, they try to use some arguments to infer the redshift of these 12 bursts. And the conclusion is that it's a bit unlikely that these are similar to 170817 because of the orientation effect, but rather could be intrinsically dimmer events or bursts at a relatively large redshift, and therefore appearing dimmer and softer for that reason.
Yeah, absolutely.
Yeah.
Okay, so I think the 5 minutes have passed as well, so maybe.
Okay, so in the last part of this lecture, I'll try to tell you something about the kilonova 2017 GFO. A warning is necessary, at least for me, because I tell you what I understood about this source as far as I followed more or less the development. Must say that it's not really, I've not been working actively in this field, so it's what I could understand from the literature more or less. Okay, so forgive me for any missing fundamental stuff and ask me or tell me in case. So I made as well a selection of what I think are fundamental facts or observations in order to understand the general picture. The situation is much more complicated. The first thing I'd like to mention is this one. Let's say we have 170817 and the kilonova, and in a moment we will see the fantastic set of observations and implications they provide. But in general, I start, if you want, with the end, about asking what other evidences do we have of kilonovae. Kilonovae were somehow called into the game even before 170817, because this is a subject that started to be developed in the 70s, and for different reasons. First, not necessarily in association with short GRBs and not even with gravitational waves. But mostly for their possible role in, let's say, contributing to the heavy elements nucleosynthesis production. And there were therefore claims of the possible evidence of a kilonova emission as let's say, one of the counterpart of short GRBs in historical bursts. So I show you probably the most known example, which is this burst here, 130603b, where, much like in the case of long gamma ray burst, there was the evidence of a rebrightening of the, let's say, emission that is sampled with the infrared images in the radar filter of, I think, the HST, images, and this excess is inconsistent with the decay of the afterglow of this event, which is a cosmological event, okay? There were other events that were claimed to have a kilonova signature like this one. So this is basically more or less the peak, and this model represented here is a modeling of the kilonova light curve, by the way. So I think now the sample comprises something like, depending on which one you choose, something between 5 and 8 events. And what is interesting is to compare, for instance, the luminosity of the optical emission or near-infrared emission of the short GRB, in which there is some claim or evidence of a possible kilonova, to that of 170817. So the idea is in this plot is that of showing that there seems to be in this distribution of ratio a quite wide dispersion of the properties, or at least the luminosities of putative kilonova present in a handful of short GRBs with respect to that one of 170817. There are upper limits, okay, but the bottom line here is that a fraction of these putative kilonovae, if they really are kilonovae, because there are other ways of explaining this possible rebrightening, appear dimmer than 170817. And sorry, while speaking, I will use 170817 without 80 2017 GFO. Forgive me for this, but it's okay, you understand what I'm talking about. And the possibility is that, which is something that probably will be assessed with the future studies and discoveries, is that the large diversity of the kilonova, possible kilonova emission, could be due to a combination of intrinsic and extrinsic effects. Intrinsic effects, as you know, in the kilonova emission are related to basically the mass, the nuclear heating of the material, the opacity of the material, and extrinsic effect in this case, especially, for instance, in such a wide dispersion, could be related to the viewing angle and orientation of the kilonova, which for the red and blue component can have, of course, a different, let's say, appearance according to the orientation with respect to the line of sight. Okay, so 170817, however, is the best kilonova we have so far, the only and best, with a really rich observational set of data. Probably the thing you know most is the fact that the kilonova was bright and fast evolving. Here you see the color evolution represented by 4 light curves, which sampled the UV, the G band, the I band, and the K band. And you see that there is a strong, let's say, evolution in the color of the kilonova, with the first early phases dominated by the blue component, mostly blue component, and the later phases instead dominated by the red one. In the insert here, you see the bolometric luminosity, which is the tool I will use in the next slide to describe it a bit more, the physical implications. So here you see what I think are, in my opinion, those observational facts that we can use in order to understand the properties of this source and the physical implications. The bolometric light curve, which is shown here, is, let's say, has a slope, is decaying as a function of time, with a slope which is consistent to t to the minus 1/3. As we will see in a moment, this is, let's say, a possible first confirm that of the fact that the emission of the kilonova is powered by the nuclear decay deposition of the elements which are produced in the ejecta by rapid neutron capture, because studies of the, let's say, nuclear decay, beta decay, and other alpha decay processes seem to, let's say, point towards this, let's say, time evolution of the nuclear deposition rate. The other plot here shows the black body temperature evolution of the fit of the spectral energy distribution at different epochs performed by different authors. They all seem to be consistent with these results, with the fact that the temperature of the black body at the beginning is quite large, 10 to the 4 Kelvin, and within 10 days it decays by a factor of 10 or less. In the plots here on the right-hand side, you see the spectrum, which is represented by the gray points, if you can see, sampled at early times, so 0.5 days. Roughly here, 4.5 days in this region here, and at very late times, 10 days or more. So the first, as I said, take-home message we have is indeed from the volumetric luminosity, since the large luminosity and the decay is a hint of the fact that the kilonova is powered by our processes, nuclear decay deposition. Let's say one outcome of the modeling of the observed volumetric luminosity is that, according to kilonova model, in order to match the luminosity, one needs, the volumetric one needs the combination of something like a few percent, like 2% of lanthanide rich with electron fraction smaller than 0.1 roughly, material with a combination of a slightly larger mass of lanthanide poor with an electron fraction larger than 0.3, more or less, material, which is indeed consistent with some simulations of neutron star mergers. If we look to the spectrum, and we look to the spectrum more or less in the central part of the evolution of the volumetric light curve, so around 4.5 days, so I'm looking to this plot here, what we see is that the emission of the spectrum is mostly dominated by the red line. The red line is the emission of the red component of the outflow. Okay, so it's the, let's say, lanthanide rich component, that one with the lower electron fraction, the smallest electron fraction. A hint that another let's say implication that we can get from, in this case, from the temperature at the very early phases, is that the temperature of the black body being 10 to the 4 Kelvin implies that more or less the source size should be 10 to the 14 centimeter. And this requires that the material that is producing the emission we see should have traveled to that distance. And this implies that the velocity at which it expanded should be relatively large, implying a beta value V over C of the order of 0.2, 0.3. The fact that the material is expanding at large velocity is also implied by, let's say, the extremely blended and stretched structures of the lines that you see, possible lines predicted by the models in the spectrum of the kilonova at this epoch, for instance. Another information that we can understand from the spectrum is related to the very early phases, because while let's say the volumetric luminosity is matched more or less with models for the kilonova, if you look to the spectrum, you see that at least the models that match the intermediate spectral distribution at the very early phases are dominated, the spectrum is dominated by the blue emission, so at 0.5 days, but that's not enough, because you see this point here is basically produced or requires the presence of some additional energy in addition to the one that is commonly thought to work as due to the nuclear decay. And this is an interesting point because, of course, this is the very early observation, the earliest observations we have for this event, but it's something which I think will be hopefully systematically explored in future events, in some future events. And so let's say that the emission at earlier phases, not sampled so far by I have a slide to describe this in a moment, not sampled so far in 1708-17 could reveal, let's say, other emission components, other sources of energy that are not required, at least for the major part of the emission of this event, except maybe for the very early phases. Okay, so I will try in the following minutes just to build a very simple model, and tell you a very simple model, which you can find in a couple of reviews like those that I presented you at the beginning, in order to understand, let's say, the physics of the kilonova that we observe. It's a toy model that tries to reproduce, if you want, the shape of the light curve, rise and decay phase, with simple argument, and the peak of the light curve of the kilonova, and tries to show how this is related to the physical properties of the ejecta. The general idea that we had, that was in circulation at the beginning, is that the blue kilonova is brighter than the red one, and they differ for the time when they peak. But the reason for this different luminosity and this different time behavior is intimately related to the main ingredients that we have to take into account when describing even the simplest kilonova model. That is the source of energy, which for the moment and also in the rest of the slides, we assume is only the nuclear deposition rate of energy due to nuclear decays. Then we are dealing with a material which, as I tried to convince you, is expanding with a, let's say, considerable velocity, 0.2, 0.3, depending on the component you consider. And possibly there is a stratification also as a function of not only the diversity, not only as a function of the, let's say, azimuthal angle, but as a function of the radius in the material that is producing the radiation. And then the radiation which is deposited with a certain rate within the material is subject to let's say, an opacity, which is the result of the chemical composition of the material in which this radiation is deposited. Therefore, a fundamental ingredient is also the opacity. From a very simple consideration, what we can think about is that you can imagine that
Giancarlo, we are now past half past midday, so I think you should slowly go to the conclusions.
Okay, so sorry, I was too long probably in.
Well, we had a lot of discussion, so.
Okay, I'm very sorry for this. I skipped the slides, but you can take a look. I try to make them very, very simple, as simple as possible, and you can also write me if something is unclear. And I'm very sorry for this delay.
No, I mean, we had long discussions, and I think this is what.
Okay, so in the slides that are following, you see I try to just report the basic ideas in order to understand the rise and decay and the peak of the kilonova with the scalings of the time and when they happens. Then I just wanted to show a simple kilonova model. You find in the review, recent one by Brian Metzger, 2020, these plots, which are very much well explained. Here, this was just to show the possible contribution at very early times by additional energy source like neutrons decay in the outer layer of the kilonova. This is something that probably you have already read. Recently, there was this paper by Balasubramanian discussing the possible rebrightening of the source. I had a couple of slides on the multi-messenger, and my last slide is before the conclusion. I just wanted to show this one because it's a kind of perspective view of the future. An exercise I tried to do was to fill this plot representing the volumetric luminosity versus time with the possible kilonova let's say, time scale when they peak, luminosity, and color, considering, let's say, the family of neutron star mergers, which are going to produce this kind of possible events, which are brighter the longer is the survival time of the remnant, which is formed, which, as you see, goes from prompt black hole formation to indefinitely living neutron star. And the part is the black hole neutron star, where you see the main game is played by the fact that you need material to be torn apart in the destruction of the neutron star, and therefore the condition is that the tidal radius is larger than the innermost stable orbit radius. Conclusion is the following from 1708-17, GRB 1708-17, and the afterglow. We have the first direct connection of short GRBs with the binary neutron star. We learned that binary neutron star can produce relativistic jets that can break out of the ejecta of the binary neutron star, which is the impeding material, if you want. The core of this jet, in the specific case, has properties similar to those of cosmological short GRBs, but it has a structure. 1708-17, the kilonova demonstrated that it can contribute to our process nuclear heating power transients like the one we observed. Let's say, main ingredients are the mass, the opacity, and the heating rate within the optically thin region. And of course, it's the dynamical evolution which determines how the light curve is shaped, becoming progressively more and more optically thin. The multi-messenger implication, I think one of these was the subject of another lecture, for using gravitational wave and electromagnetic emission as standard sirens. The other multi-messenger implications are very vast, I think, ranging from constraining the extrinsic properties like the inclination of the system to the intrinsic properties of the components like the equation of state, which there are papers by the LIGO-Birkhoff collaboration have shown, for instance, that by combining the gravitational wave signal analysis with informations coming from the electromagnetic emission, that can be as important as the luminosity distance or as informative as the prior on the spin. There can be a substantial reduction in the posteriors on several parameters like the tidal parameters or the masses of the two components and so forth, and the equation of state. So sorry, Chiara, for...
Okay, thank you very much. You don't have to apologize. There might be some other questions. This last part. Oh, please, there is a question by Eric.
I have a tangential question, Giancarlo, if you authorize me. You haven't mentioned the other potential multi-messenger observation related to 1905-21. I know this is not a GRB, this is not in your core expertise, but it's nevertheless an interesting perspective. I was wondering what is your position on this, and what you think?
I mean, no, I decided not to talk about that event because, as you can see, I could not even finish what I thought was worth mentioning. So, fortunately, I eliminated it. Well, I think this was from many aspects a stimulating event, because on the one side, the search for the electromagnetic counterparts, at least from the side I saw it, stimulated the thinking about possible ways of explaining that fast transient that at the beginning was thought could be one of the best possible counterpart, but then was demonstrated to be probably something not related to the event. I'm not really, probably you can comment more about the implication and or the difficulties in, let's say, gathering firm constraints from the gravitational wave signal alone. What I think in perspective is that probably this event, at least for what I could read and think, is an event that from the observational point of view, also from the strategic point of view of the observation, of the coordination of observation, is an event we should take as a lesson, because if you allow me to say this, I hope it's not too strong. I think what we learn in general, not only from this event, but from this experience of search of gravitational wave counterparts, which, for instance, me personally, I wasn't aware of before 2017, is that, let's say, the approach we have should not be completely independent from the expectation we have from theoretical models, which of course can be completely changed once we have gathered more and more observations, but it's at least are a good way of starting whenever we don't have enough power to be successful in the search. And on the other side, let's say the possible slightly more connection or informative channel of having the information about the putative properties of the sources quite early could be helpful, because there are some works that, for instance, discuss how informative could be having the chirp mass as soon as possible, because there are several ways of making predictions, even with a large allowable margin of uncertainties about the possible counterparts. And this could be, I guess, Susanna can correct me, could be extremely useful for the organization of at least some campaigns of the follow-up.
Okay, I see.
Thank you. So is there any other question? I see none in the chat, but maybe somebody has a final comment, or many people are saying thank you in the chat.
Yes, I'd have a final comment. I'd like to thank Giancarlo for his lecture. It was very comprehensive. And, it's a difficult exercise to collect all this number of information. And I believe it's useful to all the students that connected today. So thank you, Giancarlo.
Thank you to you, Eric. It was a very stimulating exercise.
Thank you very much from my side as well.
Thank you, Chiara, and to everyone here that remained until the end. I have a question for you. Sorry, you said it at the beginning. Can you remind me, tomorrow there is the Gather Town?
Yeah, exactly. I was about to say that. If you manage to connect, it starts around 11.
Okay, I will do my best. I will do my best to be present. I have a quite tight schedule tomorrow, but I will try to move something in order to join, because I apologize. I was not so much present during the rest of the conference, as I said at the beginning to Eric. I will try to amend tomorrow.
Thank you. That would be great. So if there are any further questions, especially on this last part of the Kilonove, maybe we can have some discussion with the students.
Thank you.
And so thank you very much then, and we then reconvene at 4